Welcome to this video on the application of the contraction mapping theorem, also known as the fixed point theorem for contraction maps, to uh, the proof of the implicit function theorem, which is a very powerful tool in multivariable calculus um, that enables you to solve in a local region um, uh, an implicit function in terms of y and x, where y and x may be multidimensional vectors, and its consequences are very deep. Here we only look at a simpler case of x and y of 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 two-dimensional vectors, where the inputs are two-dimensional vector and the output is a real number. So we've simplified things down a bit, we've watered them down, but the same ideas can be used to prove more complicated theorems in higher dimensions. So with that being said, let's get into the details. We first need to introduce what the contraction mapping theorem states. It states that if you have a contraction map T from a metric space to itself, and we have the condition that the metric space x comma d is complete, then T has a unique fixed point, and that's determined by the limit of a sequence xn in x, where x1 is said to be equal to tx0 for some arbitrarily chosen point x0 in x, and for n greater than or equal to 1, we inductively define the sequence xn by xn plus 1 equals txn. And it really doesn't matter so much what this sequence is. It's really only important in the proof of the theorem of the contraction mapping of the fixed point theorem. But what's really important is that T has a fixed point, and that there is only one such fixed point. The existence and the uniqueness are important. With that being said, now let's look at the main theorem, the main highlight of this video, the implicit function theorem. So if E is a subset of the Euclidean plane R squared, and we have a function f from E to R such that it satisfies three different conditions here listed over here. The first being that f is 0 at a particular point x0 comma y0, where this point is an interior point of E, x0 y0 is an interior point of E. Number 2, f is continuous on some open set G that contains x0 y0. And 3, the partial derivative of f with respect to y exists in G, in all of it exists at all points in G, and it is continuous and non-zero at x0 y0. So it may not be continuous in all of G, but it is certainly continuous at x0 y0, and it's non-zero at x0 y0. With these three conditions satisfied, we claim that there is some rectangle of the form m cross n, which is a subset of the Euclidean plane R squared, where m equals x0 minus alpha to x0 plus alpha, and n equals y0 minus beta to y0 plus beta, such that in this rectangle m cross n, there is a unique continuous function phi from m to n, such that the equation f of x y is solved by y equals phi of x. So phi of x, y equals phi of x is a solution to f of x y equals 0. In other words, f of x comma phi of x equals 0 for every x in M. And this is a unique continuous function. There's no other continuous function that satisfies this equation f of x y equals 0 in the rectangle M cross N. And if it holds for any rectangle M cross N, then obviously it holds for subsets of M cross N. So let's get into the proof of this theorem now. First, we need to define and fix these constants alpha and beta. So they're going to actually depend on the continuity and the differentiability of a function f. So we first know that the partial of f with respect to y is continuous and non-zero at x0 y0 and exists in G. So there must be some rectangle of the form R1 equal to x0 minus delta to x0 plus delta cross y0 minus beta to y0 plus beta, which is contained entirely in G, and G is open, so that's why it's properly contained, such that for every xy in R1, we have that the partial of f evaluated at xy minus the partial of f evaluated at x naught y naught has magnitude that is less than half times the magnitude of the partial of f with respect to y evaluated at x naught y naught. We notice that the right hand side here is just a fixed positive number, and because the partial of f with respect to y is continuous at x naught y naught, and it's defined in all of G, we can find such a rectangle in which this inequality holds. Now we set q to be the reciprocal of the partial of f with respect to y at x naught y naught, and this is well defined since this partial derivative is non-zero, it doesn't vanish, and we multiply both sides of this first inequality by mod q, and we observe what we obtain. So the mod q cancels out with the partial of f with respect to y on the right hand side, so we get 1/2 on the right hand side, and on the left hand side we get q times the partial of f with respect to y minus 1 and that has magnitude that is bounded above by half strictly. Additionally, now f is also continuous, so we in the to determine beta, we use the differentiability of f, and now to determine alpha we're going to use the differentiability as well as the continuity of f in our definition. So since f is continuous, there is an open set G that contains x naught in an open set G that contains x naught y naught with f of x not equal to y naught. There must be some alpha that is positive but is less than or equal to delta, where delta was as given here, x naught minus delta and x naught plus delta, such that for all x in the interval x naught minus alpha comma x naught plus alpha, which we set to be equal to m, we have that f at x comma y naught is strictly less than beta upon 2 times the magnitude of the partial of f with respect to y at x naught y naught. Again, we notice that the right hand side is just a positive number, and the left hand side is simply the difference of the function f at a point x comma y naught and the point x naught y naught. So we're holding y naught to be fixed, and which we're varying the x coordinate. So as we vary the x coordinate and bring it as close to, if we can bring it close enough to x naught, then we can satisfy this inequality. Because we know that f of x y naught tends to 0 as x tends to x naught, because f is continuous because f is continuous in all of G. So what this tells us now is that if you multiply again on both sides by the magnitude of q, you get that q times f of x comma y naught is less than beta upon 2, and now this fixes alpha and beta. And now we define m and n to be as in the statement of the theorem. So m was x naught minus alpha to x naught plus alpha, and n was y naught minus beta to y naught plus beta. And we define a contraction map T from the set of continuous functions from m to n to itself. Now we notice that the set of continuous functions from m to n is complete because the set n, the target, the image itself is complete because it's a closed bounded interval in R, which is a complete metric space. In other words, every Cauchy sequence in CMN converges in CMN, and we define T in such a way that for every psi in CMN, we have that T, the map T psi applied to x equals psi of x minus qf at x comma psi of x, and this holds for all x in M. So now again we need to verify that this is a well-defined map. We need to check that T is in fact that T psi is in fact a member of CMN. That is T psi, we need to check that T psi is continuous, and we need to check that the image of T psi on every x in M lies in N. So that means for all x in M, we have that T psi evaluated at x lies in N, and N is y naught minus beta to y naught plus beta. We now continue with our proof. So we know that so we first check that T psi lies in CMN. So we see that since psi of x lies in N for all x in M, because psi is a member of CMN by definition, we have that the pair x comma psi of x lies in M cross N, because whenever x lies in M, because psi of x obviously lies in N, so it lies in M cross N in this rectangle, which is properly contained in G. And whenever we have any pair of coordinates x and y that are properly contained in G, we know that f evaluated at that pair of coordinates has to be continuous at that point, because f is continuous in all of G. And so it follows that uh, in fact f now is a continuous map, because it was defined to be psi of x minus q times f of um, x comma y. So x comma psi of x. So now what we notice is that t psi is in fact continuous for all x in M. So that satisfies the first condition, that it is a continuous map. Now we need to check that the image is properly contained in N, that is y0 minus beta to y0 plus beta. And the way we will do this is that we're going to inspect the absolute value of t psi of x minus y0, and we're going to show that it's strictly less than beta, which means that t psi of x can never be greater than beta away from y0, and so it lies in the interval N. So now so in other words, we have to show that for every x in M, the quantity t psi of x lies in N. So if we fix x in M and just look at the map y mapping to f of xy for x fixed, so we look at this as a function of y, we notice that this is differentiable in the interval plus minus y0 comma psi of x, which is contained in N, because the reason we're using plus minus here is because psi of x may be less than y0 or it may be greater than y0, and we know that since psi of x lies in N, we know that the interval y0 comma psi of x is also contained in N. And whenever we have an interval contained in N, we know that it's a member of its y values correspond to a set of pairs x and y, in which a set of pair x and y that is contained in the open set G, because we formed a rectangle x naught minus delta to x naught plus delta, and y naught minus delta to y naught plus delta. Uh, uh, we also know that for all because we know that x naught minus delta comma x naught minus delta to x naught plus delta, and y naught minus delta to y naught plus delta, y naught minus beta to y naught plus beta, when we take the cross product of those two, the Cartesian product of those two intervals, we see that that subset is entirely contained in G. So for all these y values, f is differentiable, because f is differentiable in all of G. So now so we fix x in M, there must exist by the mean value theorem an exceptional point y star that obviously may depend on x in the interval plus minus y0 comma psi of x, such that it satisfies this equation. So now this equation is simply the mean value theorem applied to the function on y, which is y minus q f of xy, where we hold x fixed. So we have our two endpoints of the interval. One is psi x. So we evaluate this function at psi x, which gives psi x minus qf of x comma psi of x, and then we evaluate it at y0. That gives us y0 minus qf of x comma y0, and then we obviously subtract these two values, and the mean value tells us that there must be a point in this interval where the derivative of the same function uh, evaluated at that point multiplied by the interval is equal to the left hand side, is equal to the difference of the function at the two endpoints. That this is simply it's simply a form of Cauchy's mean value theorem. So we look at the derivative of this map, y maps to y minus q f of x comma y. The derivative of this map is nothing but 1 minus q times the partial of f with respect to y, and then we evaluate it at the point x comma y. But now if we're going to evaluate it at the point y star, x is fixed, so we are actually only evaluating it at the point y, and we are referring to this exceptional point y star, and hence we are substituting y star over here into this parentheses. And this first equation derived from the mean value theorem will now enable us to place a bound on the magnitude of t psi of x minus y naught. So we see that t psi of x minus y naught has magnitude that is bounded above using the triangle inequality into two components. The second component is simply qf of x comma y naught, and the first component is we're going to use the definition of t psi of x minus y naught. So t psi of x was nothing but psi of x minus qf of x comma psi of x. And then we also have the minus y naught, and we've added and subtracted this term qf of x comma y naught to obtain the to be able to use the triangle inequality. And now what we see is that we see that again we have the function y minus qf of xy for fixed x evaluated at these 2 points psi of x and y naught, and then we can use this equation above, which we've labeled dagger. We can use it, and we can show we can create a bound. So we know that this equation is bounded above its magnitude is equal to the magnitude of the right hand side of this equation of dagger. So we know that psi of x minus y naught is strictly less than beta, is less than or equal to beta, because psi of x is a continuous function from m to n, and we know that the magnitude of 1 minus q partial of f with respect to y at x comma y for all xy in our rectangle x naught minus delta comma x naught plus delta cross y naught minus beta to y naught plus beta, for all those points in the rectangle, we have that the magnitude was strictly less than a half by the way we chose beta and delta, which was a rectangle properly contained in capital G. And we obtained this this bound due to the fact that by using the fact that f had a continuous partial derivative with respect to y at x naught y naught, and that at x naught y naught it was 0. The function f was 0 itself, whereas the partial derivative was non-zero. So now we see that we have so this bound turns out to be beta upon 2, and the second bound qf of x comma y naught also turns out to be beta upon 2 by the way we chose our alpha, because now x lies in m, which is x naught minus alpha to x naught plus alpha, and y naught certainly lies in n. So that means that the pair x comma y naught lies in m cross n, and in m cross n, which is properly contained in G, we know that we obtained that bound that the magnitude of qf of x comma y naught was strictly less than beta upon 2, and when we add these two quantities we get beta. So what that tells us is that t psi of x always lies in the interval capital N for every x in M, because its distance from y naught is at most beta. So this entails that now t psi is in fact a member of CMN. So not only is it continuous, it also has image that is contained in N. In fact, we showed that the image is not only contained in N, it's properly contained in N. So the image can never actually be equal to y naught plus beta, y naught minus beta, because of the strict inequality over here. So that shows that T is well defined. Now we need to show that T is in fact a contraction. So this is done in the following way. We obviously need to bound the distance between T psi and T phi in the supremum metric, the supremum norm, by the distance between psi and phi in the supremum norm, and we actually find out that the contraction constant, or the Lipschitz constant that works here, is nothing but 1/2, and 1/2 works as a contraction because 1/2 is strictly less than 1, but it's positive. So we prove this in the following way. Let phi in Cmn be another function, and we see that for a fixed x in m, we again consider the map y maps to f of xy. We see that it's differentiable in y lying in the interval plus minus psi of x comma phi of x, because again phi of x may be less than psi of x or vice versa. And psi of x and phi of x are both contained in n. So this interval is entirely contained in n, and so x for uh, for for ev for every y in this interval n correspond to x in m, we have that the pair xy lies in the rectangle m cross n, which is properly contained in G, and f is differentiable in all of G. So for each x in m, we see that there exists a y prime, which may again depend on the x, in the interval plus minus psi of x comma phi of x contained in n, where we obtain another equation again using Cauchy's mean value theorem. So we consider the map of y minus q f of xy, and now we have the 2 points psi of x, uh, y equals psi of x and y equals phi of x, and then we subtract the value of the function of these two endpoints. So that's psi of x minus qf of x comma psi of x minus phi of x minus qf of x comma phi of x. This is equal to psi of x minus phi of x times the derivative of the function at some point in the interval plus minus psi of x to phi of x. Because x is being held constant, so it's only y prime that lies in this interval, and the derivative was obviously 1 minus q times the partial of f with respect to y at x comma y prime. So we have that t psi minus t phi, which so the left hand side we notice is exactly t psi minus t phi, and then when we take the magnitude, the supremum norm or the supremum over all x in m, we see that this is bounded above strictly by 1/2 times the supreme norm between psi and phi, because we again chose um, our rectangle m cross n in such a way that it was that inside that rectangle and on the rectangle, the boundary of the rectangle, the function f satisfied the fact that the equation that 1 minus q times the partial of f with respect to y for all the points in that rectangle was bounded above strictly by half in magnitude. So that gives us that the distance between t phi and t psi and t phi in the supremum metric is bounded above by half times the distance between psi and phi in the supremum metric, and this shows that t is in fact a contraction because we have the contraction constant less than 1. Also, we can now we can implement the contraction mapping theorem because Cmn is complete, um, because because n is complete, and so we conclude that there exists a fixed point that is unique to t, which we name as phi, and we see that phi is now phi is a we now first show that phi is a solution of our equation f of xy equals 0. So we are aware that for all x in m, phi of x equals t phi of x, but we know by definition t phi of x equals phi of x minus q f of x comma phi of x, and by just inspecting the left and the right hand sides, uh, we conclude that since q is non-zero, we must have that f of x comma phi of x equals 0. So it implies that phi of x is a solution, y equals phi of x is a solution to f of x comma y of x, f of x comma y of x. Yeah, because we're taking y to be a function of x. And also it is immediate that phi is continuous um, because phi is itself the image of some point in some continuous map phi. It's its own image, and every image point of t lies in Cmn, so it is continuous. And the last thing we need to check now is that this solution is unique. It's the only solution to the equation f of xy equals 0 in the rectangle m cross n. So we suppose now that variant phi is another solution for a continuous function variant phi from m to n. Then if variant phi was another solution from M to N that was continuous of f of x y equals 0, then we show that variant phi would also be a fixed point of t, and we show this is since we would have that f of x comma variant phi of x would be equal to 0, and hence t of variant phi of x would be exactly identical to the to variant phi of x on every x in M. And so that would imply that variant phi was a fixed point of t that was also a continuous function from M to N. But t has only one fixed point in the domain of continuous functions from M to N, and hence we conclude that variant phi is exactly identical to phi, and that proves that this solution is unique. So that completes the proof to this very interesting theorem. I hope you all enjoyed it, and I hope to see you in a future video. Thank you so much for watching.